Good day and welcome to One-on-One Maths Private Tutors. Today we are looking at O-Level and IGCSE Physics. The topic is liquid pressure. Pressure in a liquid increases with depth. This is because the further down you go, the greater the weight of the liquid above. In this diagram A, water spurts out fastest and furthest from the lowest wall. So we can see water goes a longer distance away at the lowest wall and slowest and nearest at the wall near the top. So the deeper you go into a liquid, the more the pressure. Pressure at one depth acts equally in all directions. This can of water has holes at the same level around it. Water comes out equally fast and spurts out equally far from each hole. Hence, the pressure exerted by water at a given depth is the same in all directions. Water emerges horizontally and normal to the surface of the container, showing that pressure produces a force in a direction at right angles to the surface. So if we have a container like this and we have a hole there and we fill it up with water, water spurts out normally, which means at 90 degrees at the beginning, then it falls. So this is the surface of the container. Third point is that a liquid finds its own level. In the U-tube shown in this diagram, the liquid pressure at the foot of P is greater than at the foot of Q because the left-hand column is higher than the right-hand one. At this point, pressure is higher than at this point because this height is smaller than this height. When the clip is opened, the liquid flows from P to Q. So when this clip is opened, because there is much pressure and there is low pressure, liquid flows from P to Q until the pressure and the levels are the same. That is, the liquid finds its own level. So they will be at the same level, and this will go down, and this level will go up. Although the weight of liquid in Q is now greater than in P, because this is a large volume than that, since Q is wider than P, it acts over a great area because tube Q is wider. So liquid pressure does not depend on weight. It only depends on depth of the liquid. In B, the liquid is at the same level in each tube and confirms that the pressure at the foot of the liquid column depends only on the vertical depth of the liquid and not on the tube's width or shape. So if we have a thin column here connected to a thick column there, if we fill it up with liquid, the liquid will find that level. If both ends are open, they will be at the same level. The weight in here is greater than the weight in there. But the pressure is the same because here we have a large surface area on which the liquid acts. Here we have a smaller surface area on which the liquid acts. So from pressure is equal to force over area. In this one, the weight is the force, it is greater, and also there is a greater area. So this will compensate in this one where the pressure is equal to force, the weight is small, so the weight is low, and the area also is low. So if now let's consider numbers. If we have pressure, force over area, force being 20 newtons over area, let's say 10 square centimeters. And here on the smaller tube, we have force being 10 newtons and the area being 5 square centimeters. Now, the same value of pressure will be 2 here and there. So a smaller area and a smaller force will maintain the same pressure as a larger area and a larger force. Pressure depends on the density of the liquid. The denser the liquid, the greater the pressure at any given depth. So now let's look for the expression for liquid pressure. In designing a dam, an engineer has to calculate the pressure at various depths below the water surface. The pressure increases with depth and density. An expression for the change in pressure, delta P, at a depth, delta H, below the surface of a liquid of density rho, can be found by considering a horizontal area A. In this diagram, the force acting vertically downwards on A, which is this area due to this liquid above, equals the weight of liquid column of height H and cross-sectional area A. So the volume of the liquid is the base area times the height. So volume is equal to base area A times the depth, which is delta H, or just H, if we consider this height to be H. Since mass is equal to density times volume, then we can substitute this volume by AH and say mass is equal to density times AH, which is our volume. Remember, this is derived from density is equal to mass over volume, then mass is equal to density times volume. Now, the weight is equal to mass times acceleration due to gravity. Our mass is rho AH, so our weight is equal to rho AHG. What we have done here, we have substituted M here with rho AH. So rho AHG is our weight. Now, pressure is equal to force over area. Our force is the weight. So the force exerted by this liquid column is the weight, which is weight over area. But our weight is rho AHG. So we have rho AHG over area A. Area cancels out, and now we have our pressure being equal to rho Hg, which we usually write as rho Gh. So pressure depends on density, acceleration due to gravity, and height. The expression for our pressure is rho Gh. So if we have density, acceleration due to gravity is a constant, and the depth of the liquid, we can calculate pressure at that depth. Let's look at some worked examples on pressure in a liquid. Calculate the pressure at a depth 2 meters in a swimming pool filled with water of density 1000 kgs per cubic meter. The value of G can be taken as 10 newtons per kg. So pressure is equal to rho GH, which is density 1000 times 10 times depth 2, which will give us the value 20,000 pascals. Pressure is measured in pascals, which we can abbreviate as 20 kilopascals. Now let's look at the mercury barometer. Atmospheric pressure is caused by the weight of air above the surface and can be measured with a barometer. A simple barometer is shown in the diagram below. The weight of the mercury in here from X to Y is balanced by the force due to the atmospheric pressure pushing down on the mercury ball. The difference in height between the top of the mercury column and the surface of the mercury ball is a measure of the atmospheric pressure in millimeters of mercury, which we call millimeters mercury. Hg is the chemical symbol for mercury. Normal atmospheric pressure is about 760 millimeters mercury. The value in pascals equals rho gh, where h is in meters, density of the mercury in kgs per cubic meters, and g is the gravitational field strength or acceleration due to gravity. H increases if the atmospheric pressure increases and decreases if the atmospheric pressure decreases. Atmospheric pressure produces a vertical force on the mercury surface, which is this surface here. Atmospheric pressure pushes this surface down. H is the vertical height of the column, which is this height here, from the surface of the mercury in this ball to the surface of the mercury in the column. If the tube is tilted, the mercury will extend further along the tube, but the vertical height remains the same. The space above the mercury tube is a vacuum, so this space here is a vacuum. Let's look at this question. A barometer which measures atmospheric pressure is filled with mercury of density 13.6 grams per cubic centimeter and has a reading of 756 millimeters. What is the atmospheric pressure? Pressure is equal to rho gh. Now, our density is given in grams per cubic centimeter. We have to change them to kilograms per cubic meter. So 13.6 grams per cubic centimeter is the same as 13.6 grams over 1 cubic centimeter. Now, to convert this to kgs per cubic meter, the grams are divided by 1,000. So we have 13.6 divided by 1,000 over 1 cubic meter is equal to 1 meter by 1 meter by 1 meter, which is 100 centimeters times 100 centimeters times 100 centimeters, which is 1 million cubic centimeters. 1 cubic meter is equal to 1 million cubic centimeters. Now, what is 1 cubic centimeter equal to x? So we can say x over 1 is equal to 1 over 1 million cubic meters. So here we have 1 over 1 million cubic meters. This is kgs. Now we go to our calculator and start with this fraction. 13.6 divided by 1,000 over another fraction there, 1 over 1 million. This will give us 13,600 kgs per cubic meter. Our height is in millimeters, 756 millimeters. To change it to meters, we say 756 divided by 1,000, which will give us 0.756 meters. Now that our units are standard, we can now calculate the pressure. So pressure is equal to rho, which is 13,600, times G, which we can assume to be 10, times height, which is 0.756. This will give us 18,600 times 10 times 0.756, which will be 102,816. 102,816, which is 103 kilograms pascals to 3 significant figures. Thank you.